All right, so we'll keep going with QP theory, and the next talk is by Alessia Franchini from Milano-Bicocca, which is going to talk about EMRI-disc crossings.
Hi, everyone. Okay, so I'll probably repeat some of the stuff that have already been said. I'll try to do it as less as possible. But yeah, I'm gonna just present our recently accepted work on QPEs production through EMRI-disc crossings, in particular to the interaction between a secondary, a companion, and a rigidly precessing disk around the supermassive black hole. This work has been done with a bunch of people listed here. So yeah, these are QPE properties. We have heard tons about it before. The only thing that I want to mention is that, as Giovanni said, there are many properties that theoretical models need to explain, need to take into account to explain QPEs. But I would argue like the very basic ones and the harder ones to get are the very high X-ray luminosities and the temperature during the QPE phase. So from the constraint on peak luminosities, you can imagine that it's hard to invoke accretion onto something that is not the central massive black hole. And also the temperature constraint is another important aspect to take into account while modeling these sources. So this has already been shown plenty of times. I just want to highlight the fact that in different phases during the light curve, there are different amplitude QPEs. And as we have already seen, the decay can be consistent with both a total and a partial disruption of 0.5 solar mass star. So these are again GSM QPEs. One of the things that I want to highlight from that is that the X-ray luminosity on the upper right panel shows a T⁴ power law dependence, and this actually might indicate that the accretion disk that is around the massive black hole is radially narrow. Because otherwise we would have also optical and UV emission from the outer parts of the disk, and so the volumetric luminosity will be proportional to T⁴ power, while here it seems that the X-ray part does all the job. So this can be taken as an indication of the radial extent of the accretion disk. There have been a plethora of models trying to explain QPEs. And of course, we have here most of the experts, and so there are, like, I would say 4 confirmed sources and then a lot of candidates, QPEs sources that have been modeled invoking tidal stripping of the helium envelope of a massive star, as well as white dwarfs on a very high eccentric orbit that fill up the Roche lobe and transfer material to the massive black hole, so invoking accretion, or main sequence stars undergoing the same mechanism, so stable or unstable mass transfer, and also multiple EMRI interaction. But what I will be focusing on is collisions between a companion and an accretion disk. This is not new. It was first proposed by Shan et al. In 2021 as a model to invoke QPEs, although with a different emission mechanism that what we actually consider. And we heard about Itai earlier, another possibility for the emission in this kind of sources. So what we do is to we develop a semi-analytical model. And we take into account a massive black hole of mass m1 with its given spin and 100 solar masses companion. We evolve the orbit of the companion using post-Newtonian corrections up to 3.5 order with leading order spin orbit. So we actually consider the nodal precession of the EMRI as well. Here in this equation, the R is the relative separation between the two objects, and V is the relative velocity. And then we add a rigidly precessing accretion disk around the primary. This disk precesses due to the fact that the black hole is spinning, and if we assume the star that was disrupted to be initially lying in an inclined orbit, which is typically going to be the case, then you will have the coupling between the two angular momentum, the black hole spin and the disk angular momentum, and this leads to Lense-Thirring or frame dragging of the orbit of the disk on a frequency which is this omega LT. If the disk, under some conditions, the disk can rigidly precess around the black hole. So this precession is nodal, meaning that it's in the Z plane, so in the plane perpendicular to the orbit, to the equatorial plane of the black hole, and it's retrograde precession. So it's a precession that occurs on frequencies that are shorter than the spin period of the black hole. So yeah, here is just, you can just don't look at the equations, but essentially this is on the upper right corner is what happens. So you have the stellar debris that are misaligned, and if the disk is geometrically thick, so if its temperature, let's say, it's higher than its viscosity parameter alpha, then the so-called warp, which is this disturbance that is driven by the Lense-Thirring effect, propagates as a wave inside the disk, reflects out of the disk boundaries, and reaches a steady state. And so if the disk is warm and narrow enough, it can rigidly precess the solid body. In the figure, you can see the evolution of the x-axis component of the angular momentum of the disk as a function of time. And this was done just using a 1D code that solved those equations for different radii inside the disk. And you can see that the disk is precessing rigidly. The disk has to be thick enough because then the disturbance can be efficiently communicated among the disk annuli. And so they can all process at the same frequency, and you can imagine that if the disk radial extent is too large, this is also difficult to achieve. So this is, for reference, is just the aspect ratio of the disk that we consider. Of course, in our model, we don't have an actual hydrodynamical disk, we just have a plane with some properties. And so, so the aspect ratio is essentially determined by M1 dot, which is the Eddington ratio of the central massive black hole, and which is somehow constrained by observations. So this will basically give us our aspect ratio that we expect for the disk. And then we know that QPE sources typically have masses between 10 to the 5 and 10 to the 6 solar masses black hole. And we calculate the precession period due to this Lense-Thirring torque that are between 1 and 100 days. And you can see that the lower the mass, the longer this precession is. And also the higher the spin, the much faster this precession is. We take the disk to have a mass between 0.01 and 4 solar masses, because there is again the indication that this disk might have something to do with the tidal disruption event. And we assume the mass to be distributed with the power law profile from the ISCO of the black hole out to 300 RGs. So yeah, and so we take this precession period and we combine essentially the nodal precession of the disk, the apsidal and nodal precession of the EMRI together in our model to get essentially the timing properties. Then, in order to produce a light curve, we need the emission mechanism. We consider something that is very similar to what ETI has considered. So we have a optical, so every time the EMRI companion passes through the disk, which due to the combination of different precession frequencies can occur between 1 and up to 3 times per orbit in very specific configurations. So every time this object just drives some material to be expelled from the disk in both directions, as we've seen before. And so basically the size of the cloud that is produced is actually, we assume, is the influence radius of the secondary object, which is given by the Bondi radius. So GM2 over CS squared plus the relative velocity square, where the relative velocity is the velocity difference between the velocity of the companion and the velocity of the disk at the point of impact. So in order to produce initial clouds of the right size to get the amount of luminosity that we need in order to reproduce QPEs, which is around 10 to the 11 centimeters, we need the relative velocities to be fairly low. And this essentially selects low mutual inclination between the EMRI orbit and the disk. Then we assume the cloud to expand adiabatically. So the radius changes with time according to this relation, where delta TQP is the duration of the QPE, and we assume the cloud to expand by a factor 3. So essentially what happens is that at the beginning, where the cloud is just the size of the influence radius, then you get the first peak, which is up to 10 to the 43 ergs per second in the soft X-ray band, as we expect in QPEs. And then as the cloud expands, the temperature drops. And so the peak transits to UV, and you don't see QPE in the X-rays anymore. And what we assume to be the temperature of this cloud is actually the post-shock temperature in a radiation pressure dominated gas. So T1 is the initial temperature of the disk at that specific location where the EMRI crosses the disk. And we can infer T2, which is the emitting temperature from the Rankine-Onyon condition in a radiation pressure dominated gas. And this E1 is the Mach number, the modified Mach number in a gas where radiation pressure cannot be neglected. And then we simply calculate why, I don't understand why it didn't change. Okay, fine. And then we simply calculate the luminosity in the X-rays, assuming this expanding radius. And the temperature during the expansion changes adiabatically as the radius increases. And we assume the cloud, so the initial temperature T2 is of the order of 10 to the 6 Kelvin for basically almost all the sources in the sample of QPEs that we model. And then the cloud temperature decreases below the quiescence level as the cloud expands by a factor 3. And this factor 3 was taken by what Giovanni showed, which is a QPE profile in GSN 069. And you can see that so basically the red dot is following the rise phase, and the purple dot is the decay phase. And you can see that the black body radius inferred from observation has changed by roughly a factor 3. So this is why we assume that the cloud to expand by that factor in that amount of time. Now, what about the nature of the EMRI companion? So as I said, we would need the initial sizes of the cloud of the order of 10 to 11 centimeters to be able to reproduce the observed luminosities, assuming that this is the machine that drives QPEs. So this naturally excludes white dwarfs and neutron stars. Using them with this mechanism, we will not be able to reproduce such high luminosities. These also exclude black holes with masses much less than 100 solar masses. So like, let's say solar mass black hole, because they never reach a required Rin. However, I should note that we take 100 solar mass black hole as a reference, but we can actually take 40 and it works as well. So, and 40 seems to be, you know, fairly common, at least in the LIGO sources. Black holes with much larger masses, as Itai has already noticed and mentioned, have a short gravitational waving spiral time, and so it's very hard to reconcile this with the QPEs observations. Stars get tidally disrupted, and so this poses a limit on the radii where the star can survive the passages through the disk and the interaction with the massive black hole. And actually, for at least two sources in the sample, the pericenter inferred from the orbital from the period between QP flares is comparable, and for one source is actually very well, it's inside the tidal radius. Plus, in 3 out of 4 sources, the star would be overfilling its Roche lobe at those radii. And so that is another thing that we have to keep in mind if we want to consider a star. And this is probably why we prefer the black hole scenario. Finally, the stellar radius is independent on the relative velocity. So basically, what is allowing us to reproduce the higher amplitude and lower amplitude peaks is actually the fact that depending on at what stage during the orbit the companion crosses the disk, you have a different relative velocity, and this gives you a different luminosity. So with just assuming that the fixed stellar radius would be hard to reproduce different amplitude. Okay, so these are the first results for GSM and EROQP2, so the two more regular sources. In the upper panel, you can see the data that were kindly provided by Riccardo and Giovanni. And the bottom panels instead show the results from our model. So the light curve that we constructed with our model. And each flare, so we assume to have a steep rise, well, almost an instantaneous rise, although this might be not ideal, and it can be modified assuming that the companion takes a while to cross the disk, and other processes, the thermalization of the cloud, the photon diffusion time scale might actually change the shape of the rise. And then the decay is actually determined by the fact that the cloud is expanding. So that is the black body emission, the black body temperature that increases with time as the cloud expands. And so after a while, you don't see the QPEs anymore. And so in both these two sources, the eccentricity that we use to reproduce the light curves is fairly low. So we have 0.1 with GSM, and I'm glad that Itai has shown the same value, and we have an even lower eccentricity for EROQP2. Of course, for EROQP2, the same major axis is a bit larger because the supermassive black hole mass is smaller. But I mean, you can see that we fairly well reproduce the alternance of low amplitude, high amplitude peaks in both sources.
Sorry, can you say,
yeah.
What is actually the main parameter controlling the relative amplitude of the peak?
Is the relative velocity between that is the main parameter, okay. Yes, and also the fact that the impact might occur at slightly different radii, so that these properties might be slightly different. And then we try to reproduce the more irregular sources, and this was actually a bit harder. EROQP1 has shown this behavior, and if you believe that there is a somehow superposed superimpose long-term periodicity, then we reproduce this long-term periodicity with the precession of the disk, actually. So this clearly, so this might be an indication of the fact that these three precession frequencies are actually playing a role all together, and depending on how they combine, you get different types of QPEs signals. And the harder to reproduce was RxJ, as you may expect. It's the most exotic, source, where you have this alternance of high amplitude and small amplitude peak that are very close in time. And we had to increase actually the eccentricity for this one, and the eccentricity is 0.4. And as I said earlier, the semi-major axis that we need in order to reproduce this period is 50 Rg. So you can imagine that this is somehow inside, or at least up the tidal radius for a solar mass star, given the mass of the main black hole. So it would be hard to produce this. Now, these are the effect of since we have many parameters in our model, it's important to understand what are the main effects of some of them on the light curve, and especially on the timing properties. So if we, what we did was to take the GSN synthetic light curve that we reproduced, and we changed one parameter at a time in order to understand what is the effect that this have on the timing properties and also on the emission. So initially the spin we took was 0.1. If we take a higher spin, which I believe is 0.6 on the upper left corner, then you can see that the timing of the peaks is off. And this is due to the fact that the spin essentially controls the precession frequency of the disk and also the nodal precession frequency of the EMRI. So changing that will change the interplay between the frequency, and also it will change the amplitude of the peaks. Then if you increase the eccentricity, then you get something that is more similar to what we see in RxJ, so a higher amplitude peak followed by a low one on a very short time scale, but then the luminosity drops significantly. And if you consider retrograde EMRI, so high inclinations between the EMRI companion and the disk, then you never reach the luminosities that are required. So this is like 2 × 10⁴, so it's too low to be detected. And so we can rule out retrograde EMRIs, at least for our model. And then if you switch off disk precession, because typically it will occur on a timescale which is a bit longer compared to the other 2 precessions that are at play, then the timing doesn't change very much for this source, which is one of the most regular ones. And but it will change definitely the amplitude, the absolute amplitude of the peaks. So we'll get lower. Now, all this is very nice, but it's just a semi-analytical model. So what we would like to do is to understand whether hydrodynamical simulations can give us something similar. And this is just to show you, this is a hydro simulation that for a slightly different system, because the mass ratio was slightly different. And also we here just plot the accretion onto the companion, which is definitely not what's happening in QPEs. But this was just to show you what is that the scenario in hydro is much more complicated than that, because the disk might also become eccentric, and so you will add further the upsidal precession of the disk. So we'll have 4 frequencies that play a role, and this is just the bottom one. The bottom panel is just to show you that you can imagine that to have between 1 and up to 3 outbursts on the secondary object, just because of how because the companion can intersect the disk at both the nodal the ascending node and the descending node, and also at the apastron of the disk, since the disk is eccentric. But again, this is just an example. So we are now running the first test of the interaction between a 100 solar mass companion and an accretion disk around a massive black hole. So this is using Gizmo in MFM mode. The mass ratio is 10 to the 4. We add radiation pressure. We add black body cooling of the gas. And we use GSN parameters just because this is the most well-studied source, and just to start with this. And most importantly, the dynamics of the binary includes 2.5 PN corrections to the motion. So upsidal precession is taken into account. Gravitational waves are also taken into account, although these distances, they will probably not modify too much the orbit. We still need to add the rigid precession of the disk. So the disk is now coplanar with the spin of the black hole. So the black hole is, the central black hole is not spinning, neither is the secondary. But essentially what we obtain, so this is the first crossing, this is the second, their orbit. So it's so this is actually the same simulation, but viewed edge-on. So this is the Z-plane cut of the crossing. You can see that the first crossing produced disperse on both sides of the disk. The second cross is actually much milder than that. So we really need to understand that why in the first video that I showed, it seems that it seems that the first pericenter passage just punches a hole in the disk, and the disk takes some time to refill it. And then we need to investigate more what happens during the second passage, and why the emission seems to be a little bit fainter. And this is very preliminary. So it's just the first test to understand what is happening. Okay, so my conclusions on this model is, so it seems that our model that invokes a rigidly precessing disk and a 100 solar mass EMRI companion works fairly well for if we assume a prograde orbit with low inclination with respect to the disk. One might say that low inclinations might be constraining a very narrow region of solid angles, which is true. It's just only 2%. But first of all, we don't see that many sources. So that might be a clear indication that there might be an effect, a selection effect. And second, even if let's say the inclination was initially, the mutual inclination was initially higher, then we would not see QPEs because the relative velocity would be too high, and so the QPEs would be too faint. But then as the EMRI and the disk interact among each other, it's natural to expect that the mutual inclination would be damped with time. So they will at some point transit through this low inclination regime before aligning possibly at the end. And so that's where we see QPEs. Then of course, if they are aligned, we don't see anything anymore. And then as we saw, the combination of upsidal and nodal precessions is able to reproduce the variety of QPEs behavior that we've observed. We assume the emission to be generated by an optically thick cloud of gas that expands adiabatically and emits the black body. And these seem to work fairly well in reproducing the correct temperatures and luminosity that we need. But of course, more investigation of this with simulation is definitely required. One of the things that I want to highlight is that it seems in our model that the temperature ratio decreases. So the ratio between the QP temperature and the quiescent temperature decreases with increasing quiescent rate. And this seems to be consistent with what Giovanni showed you this morning. So the ratio between this temperature tends to 1 when so basically when the quiescence rate increases with time. And of course, if this model can explain almost all the detected QPEs, then we will have important conclusions or consequences or limits, possibly on the characterization of the EMRI population. And it's a bit optimistic, but yeah, I'll leave you with that. Thank you for your attention.
Yeah, so I guess for the TD case, if you've got a precessing disk, then one of the predicted observational signatures is the modulations of the soft X-ray emission. So should we be seeing something similar in QPEs in quiescent state? And if we're not seeing that, can we say anything about like the inclination angle to the system?
That's an interesting question. I don't believe there is such a, well, the QPOs might be an indication of precession. I mean, observers can correct me.
But those are the sources apart from maybe 1 or 2. Don't have to be updated even tests. And one, which is 69, and there are these QPOs, and for the other RxJ, some people are playing QPOs in crisis during one epoch and not in the others. It's not very significant.
But these like the QPOs are lower frequency than the Lense-Thirring or the disk precession frequency. So we would see it over longer time scales. I guess if we monitored the disk, say for example, XRT.
No, if Giovanni is still online. Maybe.
Yes, actually, I think, I mean, we are looking for these long-term trends in our data. So we are missing a few observations, I would say, in the sense that we don't cover well enough the time span of the expected, let's say, from 10 to 100 days for the precession, either the orbital or the disk precession. But we have indications. So we are actually refining our analysis, and it could, I think, I mean, obviously detecting, for instance, orbital precession consistent with one of these orbital models that are coming out either from black holes collision or star collisions would be really probably a smoking gun signature for this kind of effect. So we are working hard on that, and stay tuned, because I hope that we can get some nice results on this long-term variability.
So you mentioned the fact that the orbit of the star may align with the disk over time. So do you estimate how long will this phase in which your model is able to produce QPEs, how long will it last? And what does that imply on rates?
Well, okay, so that's very hard to do with the semi-analytical model. I can tell you that the time scale over which the disk will align with the black hole are long, and then I'm not sure what happens to the EMRI. I mean, you know, yeah. I mean, so I don't think we can say much.
Right. So it will take a long time, but then, yeah, the question is, you know, what fraction of the time does it spend in this favorable?
It will be another thing to actually investigate with the simulations to understand what is the.
And also just a small comment is that the fact that the flares are, their amplitude is modulated, so it's not only the recurrence time but also the amplitude. So this is just I think a feature that our model is also able to produce if you consider the fact that these two blobs of gas are not entirely symmetric. So depending on which side of the disk you're on, one flare might be fainter than the other. Yeah, so just a comment.
My understanding is that the GSM 069 and the University QP2 show the alternating period. So can you avoid that in your model? So I guess in your model of the University QPE1, do you get alternations in the recurrence time between adjacent flares? How do you kind of get out of that?
Okay, so how do I get from these regular ones to these irregular ones?
Yeah, especially
Is
if
that
I
right?
just take 4 flares in a row.
Yeah.
It seems the precession times are long compared to the orbital period.
That's
So don't you necessarily get the alternating pattern in this case?
Okay, so in this case, for instance, the precession of the, so we had to change the parameters in order to get a precession of the disk on a shorter orbital time scale to explain the modulation. So we have 8 parameters in our model that we can tune to have to produce different light curves. And so, I mean, you can change the parameters that regulate essentially the frequencies of precession in order to get different behaviors.
But it seems like to get rid of the alternating long short, you have to make the precession time comparable to the orbital period, which is pretty challenging.
But also EuroQP1 has one of the longer periods. So it's like 18 hours. That's
Yeah.
the time between flares. So the actual period is 36 hours. So, you know, of order days. So maybe the upside precession timescale is could be comparable if you.
But it's always longer by some semi-major axis
Right.
over RG.
Yeah, I mean, depending on the
So,
black hole mass.
yeah, exactly. It seems like it's always long.
Right. Yeah.
Depends on how eccentric it is. I mean, if
Yeah.
you.
Agreed, if you make it, so I think that's the wiggle room, is if you make it sufficiently eccentric, then you have more freedom.
If you make eccentric, though, you get something very similar to this. If you use the same eccentricity for EOQP1, you don't get that light curve.
But just to note, the EuroQP1 is most likely doing something more complex than what we see with NICER. Just because expanded have revealed a little bit,
Yeah,
even
that's
of
the other
weaker
point.
bursts.
Yeah.
Could be the more long-lasting version of what RxJ occasionally is doing, and NICER would miss some of the fainter ones. So all this might happen in between. So the eccentricity you are using here might not have to be the one. Well, what would happen if you left everything the same way, but for instance, you use an eccentricity like 0.4? Can we use maybe the comparison plots to try and
Yes.
picture it?
So you get lower amplitude peaks.
All of them are lower, or do you get higher contrast? Do all of them get lower, or do you get a bit more diversity in the amplitudes?
Well, in this case, they all get lower.
Okay, so it has to be a combination of things that
Yeah.
we can think about it
Yeah, I
later,
mean,
yeah,
it's
but
yeah.
I understand that we're not fitting data yet, but also because
No, exactly. I mean, what we want to do ultimately is
Yeah.
to feed the model into an MCMC or nested sampling algorithm
I
to
know.
infer the parameters, because there are that many, they're not constrained, most of them. So it's
right. So we have a lot of data for EuroQP1. It's just a bit hard for me now to tell you. Well, I can't claim that I can tell you how many bursts exactly there are in the data.
but also the fact that you show that one single burst can be fitted with multiple light curve. And that's something that we actually were able to reproduce when we were tuning the parameters, because for some combination of the frequencies, then you would have peaks that intersect between each other. And so that will give you a weird shape peak.
What regulates the duration of a burst? The duration. Would you have any, like, would it be like a bigger black hole with a bigger cross section and a bigger cloud? Or I guess that's probably true for both models.
Yeah.
That makes sense. So how do you, for instance, how do you get to durations which are half an hour compared to durations of several hours in a burst? Like,
Oh, that's an assumption of our model. Like, assume the expanding factor to be the same. We just change delta T to the source we are modeling.
so it's not about the size of the
So
cloud.
it's nothing like properly to become, I would say.
In our model, the duration of the flare is set by the diffusion time of photons from this expanding ejector.
So you can change by a factor like that.
So, well, factor of 10 is perhaps a bit challenging,
It's very
but yeah, I mean, you will expect to have some variations also depending on right? And there will be some precession over time, and yeah, you will be probing different parts of the disk.
Also, another factor than the same source, like across different sources.
Oh, yeah. Yeah, well, I think that is sort of reasonable, you know, for different black hole masses and different M dots.
Two things. First of all, if you're talking about mutual inclination, but in general, even if they were started out with a small mutual inclination, since the precession frequency of just a particle on a geodesic is going to be different than the kind of rigid body precession frequency of the disk, you know, they wouldn't stay, you know, with a small mutual inclination. So you might see, if the inclinations were nearly, you might see kind of beating with the relative, you know, nodal precession frequencies.
Yeah.
And also, if you think about the argument of pericenter, which is, you know, evolving due to apsidal precession. So when it's zero, you'd think you'd have equally spaced, you know, for taking for a moment of a kind of an equatorial disk, you'd have equally spaced things.
Right.
And when it's either, you know, a multiple of pi over 2, they'd be equally spaced. And then, but of course, when it's 0 or pi, one of them is going very fast, and so you'd have a high relative velocity. And so seeing as you had apsidal precession and as that apsidal angle evolved, seeing both the kind of changes in the relative durations and the amplitude. I mean, I would think that'd be kind of a very smoking gun signature of this kind of thing.
Yeah.
I don't know. I mean, if you can kind of see that, but.
Well, we did some tests in the early phases where we just switched off one precession at a time and, you know, checked that everything was as we expected, and it was. But yeah, we surely can definitely go back there and check. Yeah.
I mean, as long as you had enough of these things, I think it'd be very predictive, this model. I mean, it's a good feature.
So I just want to make sure I understand the model. So the disk is from a TD.
Yes.
So those disks, so you're saying that you have a supermassive black hole, and so this 100 solar mass companion is a black hole.
Yes.
Right? Yeah. Okay. So, and then, so my question is really specific to like, what are the things that you can tune? Because the disk outer radius, you've chosen to be all the way out to 300 RG. But is that justified for TDs? Like, do the disks extend so?
Well, that's one thing for sure. So people typically assume the TD debris to circularize at 2 times the circularization radius, right? Which is order of 100 RG, 150. If that was true, then we wouldn't get passages, because even for apart from RxJ, otherwise we have the constraint on the recurrence time between different peaks basically determines the semi-major axis of the orbit. And so for the other 3 sources that would be outside of the disk radial extent. However, I do not think we are completely sure about where the debris will circularize, whether the disk will not spread, or I mean,
it will spread. I mean, this will viscously spread.
Yeah, exactly.
Whether that's the
of course on the
explanation for why we don't see QPs earlier.
right, yeah.
So you should
It might be also one of the reasons that we don't see QP earlier, because the disk is narrower.
But the disk should align at some point as well.
Yes, it will.
So going back to the TDE QPE connection, so initially you have this misaligned disk, and then I guess it has not spread far enough, so you don't see QPEs. I guess at some point it spreads far enough, but by that time, maybe it's probably already aligned with the black hole, because if you go back to your own paper, you know, the time scale, Nick Stone's paper, there's a plot on how long it takes for a given black hole mass to align, and the alignment time scale is really like less than a year for like the range of black hole masses, right?
No, I wouldn't say it's less than a year.
Yeah.
It won't stay rigid though. As you
Yeah,
think of it,
so
the
it
further it
won't stay
spreads,
rigid.
so the outer bits could stay misaligned, even if the
Yeah.
inner bit, you know, became equatorialized.
And yes, that's the other thing, like we assume rigid precession, but what can actually happen is that the disk is precessing differentially. So you are in the diffusive regime, And so you have the inner parts that are aligned, the outer parts that are misaligned. The shape of the disk, it would be something more complicated than just, but it's, I mean, as you can imagine, it's not super straightforward to plug this into a semi-analytic model. So
the outer disk will never be aligned in this model, or
Say again?
the outer disk is always misaligned?
Yes, like that's what we assume. It will also depend on the viscosity, which really is something unconstrained.
Sorry.
I'm trying to understand what can be done from the shape of the piece, and some questions in a way is controlling the sharpness of the rise, and also for the people doing observations, if at the peak, I actually would like to understand how symmetric is the rise and the fall. Is that they symmetric? Because it looks to me
Not much, no.
not much.
No, it's
Not really, it's not really.
So does it rise faster than it decays?
always, yeah. Or like when the bursts are short enough that you can't really get a fit of a longer decay than rise. Sorry, when you don't get a statistically from a fit that the decay is longer than the rise, it's most likely because the flares are short and the Gaussian is good enough to fit those data. That's my hunch. The longer the burst gets, the more asymmetric they look.
I guess I'm trying to understand if I understood correctly. I'm trying to understand this can help discriminate the two models that we have today. If I understand correctly, if it's mostly the cross section of the object that is plunging to the disk. If the cross sections are the same, it doesn't matter with the black hole, it will be the same.
That's my question.
That is correct. Yeah, that is correct.
So I guess now by definition, you want to model the spectra. So whatever orbital you get, you want to reproduce the spectra. So we're not using now data to predict what the orbital is. But is there any, apart from the fact that stars could get disrupted or overflow, is there any reason as to why they have to be all stars or all black holes, or can they be either?
One clue would be considering the rates of these two different flavors of the models. That's why I was also asking about.
Which are super uncertain, like what are EMRI rates? People are still arguing about them,
Right, but we
so I
can,
don't know.
we need to do something, right?
Yeah.
So we can estimate that. I mean, the arguments that I showed, we think we're in the right ballpark in terms of how long do these EMRIs survive, and the abundance that is observed. So I think that is one sort of way to distinguish between the two flavors. And I think, sort of things we've been seeing in GSM 069, this possible additional flare, whether it's related or not to what is happening to the EMRI, right? In the black hole case, the EMRI cannot provide more mass. It cannot contribute to the flare in terms of mass budget. So I think, trying to understand that part, might help us distinguish.
Yeah, in this respect, if I can add something about exactly what you said on GSN. So let's say the new observation will show a variation in the period. So in the period in this context of the collision, so the period must be twice the average recurrence time between the QPEs. If a new observation will show a change in period, I think that the black hole can be safely ruled out, in the sense there is too much energy in that orbit of 100 solar masses black hole to change the period due to an interaction or whatever. So in that case, a star would be favored, I think. While if you only change let's say the QPEs the timing of the QPEs that this in the middle, this can be changed either by eccentricity variation or even by inclination variation. So if you have a TD, another partial TD that comes in another direction, the disk will have initially at least a different direction, and so could change the relative timing of the QPE that is in between. But if we see a real period change, I think that a black hole would be tough because too much energy is in the orbit, I think.
Thank you. Sorry. If you want to be on time for lunch, I think we have to stop now and go to the next talk. But keep your questions in mind for the discussion this afternoon. And thank you.